we are going to talk about logarithmic differentiation. What the heck is logarithmic differentiation? All it is using logs to take the derivative. You build a cabin, you sit inside the cabin when it's nice and warm, and then you just do the math. No. So using logs to take derivatives, what does that mean? Well, maybe the best way to illustrate it is with an example. Or not, but I'm going to do an example anyways, I don't care. Alright, suppose we have f of x equal to x raised to the x, and we're supposed to find f prime of x. Now some people are thinking, oh, well, maybe I use the power rule with the chain rule. However, we can't do that. Admittedly, why can't we do that? We can't use the power rule because this right here is not an it's a variable. It's not a constant number. It's not some number. So then, well, what about if we used, well, we actually, the normal thing, don't write this down, the normal thing that we take the derivative of is e to the x, but we can't use that and chain rule because we don't have a base that is e. So this also doesn't help. So what do? I think we just stop. That's the end of this video. See you guys later. Just kidding. What do we do? The trick, here's the trick. Whenever you have x in the exponent, you can take the natural log of both sides. Maybe write that down. All right, so let's actually get into this problem. Enough writing the tricks down. We're gonna do the actual problem. So my first step is to change the f of x to a y, just so it's easier to write. So f of x is the y, and then x raised to the x. Now the trick that I'm telling you is to take the natural log of both sides. So I'll have the natural log of y equals the natural log of x raised to the x. I see why you did that. Now you can bring the exponent down. You can bring the exponent down. So that comes out there. And what do you have? You have the natural log of y equals x times ln of x. So why do we do this? Well, now we can use implicit differentiation to find dy dx. Because the derivative of y is the same thing as the derivative of f of x. So we'll use implicit differentiation here and solve for dy dx. So I'll take the derivative of that would be 1 over y, the derivative of the outside, that's the derivative of the natural log, times the derivative of the inside, so you tack on a dy dx. Remember, they don't agree on the bottom, so you got to tack that on. And then here I use the product rule. First function is x, the second function is natural log of x. So first d second plus second function, ln of x. D first, the derivative of x is just 1. And I will simplify a little bit. 1 over y dy dx equals 1 plus the natural log of x. And that's just because those canceled out. So we're almost done. I'm going to solve for dy dx by multiplying both sides by y. And what do I have? Well, that goes away. And I have dy dx is equal to y times 1 plus the natural log of x. But something's weird. Why? I have a y in there. And that's weird. But I don't have to have a y in there because I know what y is. So here I'm going to substitute back for y. Or not substitute for y, but substitute whatever I have in place of y. So there you go. That's the derivative. That's f prime of x. The whole point was to take the natural log of both sides so we can move that exponent down. And then once you do that, we can do implicit differentiation. So that's pretty cool. Let's take a look at another example. Alright, maybe you should pause this and try it on your own. We have h of x being sine of x raised to the x power, and we're supposed to find h prime of pi over 2. Now that means take the derivative and then plug in pi over 2. However, we do have an x in the exponent, and every time you have the x in the exponent, what does it say? Whenever you have x in the exponent, you might want to take the natural log of both sides. And that's what we did here. Then we can use implicit differentiation. So let's see if that works out. You might want to pause it at this time. I'm going to finish it now. Okay, here I go. So h prime, well, I'm going to first change that to a y. That's the first step. And then sine of x raised to the x, and then I'll take the natural log of both sides. Once I have done that, I will move that x into the front, and then I will use implicit differentiation. So what does that mean? Well, that's 1 over y, right, because that's the derivative of the outside with the inside the same. Usually the derivative of the natural log of x is 1 over x. But then we got to multiply it by the derivative of the inside, which is dy dx. You tack on the dy dx. And then that equals a product rule with also a chain rule. So we got to do, well, that's the first function, and then the second function has the chain rule in it. So first, d second, the derivative of the natural log of sine of x, well, that's the derivative of the outside with the inside the same. 1 over, sorry, not the natural log, 1 over sine of x, because this is the outside, that's the inside, times the derivative of the inside, that's times cosine of x. First d second, so that's first d second, plus second, which is the natural log of sine of x, second d first. The derivative of x is just 1, so it's times 1 there. And then I'll tidy some stuff up. I'll tidy it up. And I'll multiply both sides by y, which, be careful, you have to put parentheses around that, times y. Maybe I'll put a y there. Times y. Y is the same thing as sine x raised to the x power, so I'll change that in the next step. So maybe I'll move this over here. So I have that. I'm going to change the y to a sine x raised to the x. But dy dx is the same thing as h prime, right? Because I turned the h of x into a y, so dy dx is the same thing as h prime. So I'll change that. Don't forget the parentheses there. Now I need to plug in pi over 2, right? So h prime of pi over 2, yeah, that's what I'm finding, equals, well, sine of pi over 2. Sine of pi over 2. What is sine of pi over 2? That's 1. So we have 1 raised to the pi over 2. And then times all of this stuff. So that's just 1 right there. That's just 1. So that's nice. I have pi over 2 times, what's cosine of pi over 2? That's 0 over 1. So that whole thing goes to 0. This goes to 0. Cool. And then plus the natural log of, well, sine of pi over 2, that's just 1, we said. And the natural log of 1 is also 0. So I just have h prime of pi over 2, that's just 0. That wasn't so bad. Took longer though. Yeah, there you go. I'm going to be done with this video. Goodbye.